All right, gang, Math 5500. Just review from the last video. We focused on variation, and we looked at first of all we looked at the variation just of the y's. We defined that to be the sum of squares. When we started focusing more within the distribution at a set x sub I, we were looking at the variation of the predicted values or the errors, and we defined that to be the sum of squares error. Now, notice in both of these cases, to move that into what we call mean square, either the mean square or the mean square error, we just divide by the degrees of freedom. All right, completely shifting gears now. We want to look at inference for our betas. And if you recall, statistics has a whole lot to do with examining the relationship between samples and populations. In the inference setting, we start out with a sample that is known, and we use it to estimate something in a population that is unknown. Well, again, this is the definition of inference. For example, if we had an unknown population mean that we wanted to estimate, then it would make sense to take a sample mean, x bar, and use it to make that estimation. Well, in the regression world, it turns out that beta 0 and beta 1 for our parameter model, for our population model, are generally unknown, and we use beta hat 0 or beta 1 hat. Sometimes we just call this B0 and B1 as the values that we use to estimate the unknown beta 0 and beta 1 for the parameter model. Now, we saw before that in a previous model that another way of calculating beta 1 is to look at the sum of the deviations for x and y and divide by the sum of the deviations squared for x. This can be taken into the fact now that we know that beta 1 forms a normal distribution with mean beta 1, I should say, yeah, these B1s, and variance sigma squared over the sum from x sub I minus x bar quantity squared. Now, the proof of this is relatively sort of easy, I guess. I don't know. Let me get organized here a little bit. But we can start out, if we're going to prove this, to show that beta 1 can always be rewritten as a linear combination of some k sub I times our y sub i's, where you can prove that this k sub I that does the trick is this value right here. Now, from this, we can conclude a couple of things, or summarize that the sum of the k sub i's will be equal to 0. The sum of the k sub i's times the x sub i's will be equal to 1. And the sum of the k sub i's squared will be equal to 1 over the sum of the deviations. So kind of tattoo that to the brain. Don't take up a lot of brain space, but just have it at your disposal. Now, I want to focus now. I want to shift all this into, and we're going to use this stuff, obviously. I'm just not wasting your, or at least I hope I'm not wasting your time. So I want to focus, switch gears on defining the distribution. of our B1s. Now, when I define a distribution, the first thing I want to define is the shape, and the second thing I want to define the parameters that define that particular shape. So what I hope to find is I hope to find that I got a normal distribution, because if I have a normal distribution, I know a normal distribution is defined by its center and its spread, namely its mean and its standard deviation. So if I can prove, if I can convince myself that the distribution of beta 1s is normally distributed, then I just get tunnel vision on, well, what's the expected value, what's the standard deviation, and I go from there. So it works out nicely, because we know that the y sub i's are normally distributed. And independent. Now, that works out nicely because we also know that any linear combination of independent and normally distributed variables are, drum roll please, normally distributed. That makes me happy. All right, I hate to sound like a big old nerd here, but that makes me happy, because now I know that my shape is defined. I have a normal distribution. Now I can put tunnel vision on the two characteristics of a normal distribution that define the normal distribution. What's the center and what's the spread? Once I define my center, my mu, once I define my standard deviation, my spread, I have totally defined my normal distribution. So the first thing I want to do is I want to focus on what's the mean. Now again, don't lose sight of the bigger picture. What I'm trying to focus on here, what I'm focusing on here, is I'm focusing on the distribution of the beta sub i's. Because, all right, let me pump the brakes a little bit. Something may not be relatively clear. So I go out and I want to use beta 1 to estimate, I want to use B1, what I get from a sample, to estimate beta 1. But this B1 is just one random sample out of many. So if I repeated this, so I go out and let's say I set in and I collect a random sample. Well, for the first sample, I can calculate the slope. All right, throw those back in the mix, pull out a second sample, calculate a slope. We expect these to vary. That's why we'll talk about the variation of the sampling distribution of B1. And just complete this, continue this forever and ever and ever. Repeat, 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 and so on and so forth. Well, these numbers right here, these beta 1s that would be calculated from different samples, is called the distribution of my beta 1s. So what we want to know is all these numbers that are certain to have variation, they're certain to have a center measure, a measure of central tendency. Well, what are they? Well, right now I want to focus on what is the mean. Well, the mean is just going to be equal to the expected value for beta 1, which from before is just equal to the expected value of the sum of the k sub i's times the y sub i's, which is equal to the sum of the k sub i's times the expected value of the y sub i's But we know that rewriting this, we have the sum of the k sub i's. The expected value of the y sub i's is just beta 0 plus beta 1 x sub I, which is distributing the k sub i's, beta 0 plus the beta 1 sum of the k sub i's x sub i's. Well, from before, back over here, we know that the sum of the k sub i's is equal to 0. And we know that the sum of the k sub I x sub i's is equal to 1. So the mean, or the expected values of the b sub 1's, will just be beta 0 times 0, beta 1, or I'm sorry, b1, which is exactly what we hoped that that we would find. Actually, I think that would be beta 1. These should have been actually beta 0. I didn't notice that until it actually came out of my mouth. So expected value would be beta 1. Now, what's the variance look like? What's the spread look like? What's the variation look like? Well, we want to focus on the standard deviation. So the variance of beta 1's, so all these beta 1's over here we talked about, if we can put all these in our calculator, calculate the standard deviation and square it, well, what would that value look like? Well, from before, it's going to be beta 1 can be rewritten as the sum of the k sub i's, y sub i's, which is equal to the sum of the k sub i's squared, sigma squared, sum of the y sub, or the variance of the y sub i's. Now, this will be equal to the sum of the k sub I squared times the variance. Pull the variance out times the sum of the k sub I squared. We know from the previous page that this will be equal to sigma squared, which is equal to 1 over the sum of the deviations squared. So our estimated variance of all these things up here will be equal to sigma squared over the sum of the deviations, and we're going to estimate sigma squared by the mean square error. So, ladies and gentlemen, the variance of these will be equal to this. We know further that we define a standard deviation not in terms of its variance, but its standard deviation. So, of course, the square root will be the estimate, which is the estimate of the population standard deviation for B1. So, drum roll, we know that the test statistic in the inference setting, of course, is going to follow a t-distribution. taking our estimate for beta 1, B1, minus the hypothesized value for beta 1 over the standard deviation with degrees of freedom equals n minus 2. It follows that the confidence interval can be calculated by taking beta 1 plus or minus the t critical times, all right, I can't stand that. B1 plus or minus the t critical times S for beta 1. Now, in the next video, I'm going to go through an illustration of this and show how we could carry out test statistics, calculate the p-values, and calculate a confidence interval too. So we're going to use all the stuff that we created in this video. So I'm not really sure why I had this up. I'm trying to keep my videos at around 20 minutes. When I first started creating videos, I had a target of 1 hour, and I found that that's just too much. I was doing a lot of talking that you might say, well, that's what you're doing right now. But I was doing a lot of talking and it really didn't matter. And so anyway, I'm trying to restructure things to where videos are about 20 minutes. So next video, we'll put all this to work, and actually I'll show you how to carry out a test of hypothesis and calculate a confidence interval for B1. All right, take care.